the third keynote speaker, which is Marcos Mandado from the Physical Chemistry Department of the University of Vigo in Spain. He's also a long-standing friend of me, and he's a computational chemist, and his research activities mainly focused on the study of molecular aggregate and intermolecular interaction from a point of view of the electronic structure, and also from the point of view of the dynamics, especially concerning the characterization of the intermolecular interaction, which, by the way, is precisely the topic of today's Marcos lecture. So I hope he will give you an idea of what is one of the typical activities of computational chemists. Okay, please, Marcos. So just an information about the trip to the gala dinner, which will be by bus. And please do not forget that the departure time is 7:30, okay? Otherwise, if you miss the bus, you miss the dinner. Okay, see you this night at dinner, okay?
Yeah. Can you hear me?
Yes. Okay. Well, thank you. Well, after many problems, I think I can give my talk now. Okay. Well, first of all, thank you, Andrea, for the nice kind of introduction, and thank you to the organizer for inviting me to be here. It's a pleasure, and I really enjoy my stay here in Athens. Well, since this is a highly multidisciplinary audience, I have tried to prepare a presentation accessible to people who is not specializing in computational chemistry. But I can avoid to. I think it's not working. Doesn't work well. Okay. Batteries. Low battery.
Okay.
Oh.
Switch off.
Anyway, I have to move around here.
Okay, it's not that bad.
Yes. Okay. Well, I was saying that I have tried to prepare a presentation accessible to people who is not specialized in computational chemistry. But of course, I can avoid to introduce some theory regarding the methodology I'm going to present here today and the implementation we have done in a software tool in Vigo. Well, my presentation is about the study of non-covalent interactions by means of molecular dynamic simulations simulations following a systematic and rigorous way based on the combination of classical and quantum physical laws. So this topic that would seem very specific is, in my view, of general interest because these interactions regulate many important aspects of life, like, for example, the conformation of proteins, the secondary structure of DNA and RNA macromolecules, and the transport of substances within our body, and the delivery within the cells. So all of these biological processes are covered by these intermolecular interactions, non-covalent interactions. So understanding these non-covalent interactions in detail, so it's crucial to understand the biological process. And for example, design new compounds, chemical compounds with improved activity, pharmacological activity, or, for example, drugs with less toxicity. So it's very important topic for us. Well, this is the outline of my presentation. I will start with a brief introduction of molecular dynamic simulations, both at classical and quantum level. Then I will explain how to merge the main virtues of both methodologies, classical and quantum, in what we know as multi-scale modeling, and in particular in the hybrid quantum mechanics, molecular mechanics methods, QMMM, some abbreviated. And after that, I will introduce the different type of non-covalent interactions we have, and the way to investigate these computational, these non-covalent interactions using quantum methods in gas phase, and the way also to introduce the effects of the environment in condensed phases by classical mechanics. Well, after that, I will present our methodology, we'll explain our methodology and the implementation we have done. And finally, if I have time, I will show you some examples, because I don't know if I will have time to reach the last point. Okay. So let's start then with the classical molecular dynamics. So classical molecular dynamics, the nuclei move under the action of different forces, which are represented with different terms in what we know as the force field. Okay. Well, here we are just interested in these last three terms, this one, and this one, because they account for the non-covalent interactions. Okay, so if the interaction has an electrostatic nature, then involves the permanent atomic charges system. Okay. But also we can have a polarization of these charges, okay, due to changes in the atomic environment, which is called the polarization energy, okay, or the interactions can originate in the no quantum phenomenon called as Pauli repulsion and dispersion. Okay, these are quantum effects that classically cannot be represented in principle, but normally in the force fields, you try to represent as much as possible to reproduce these effects using analytical potentials like this potential, which is called the Lena-Jones potential. Well, all these terms make up what we call non-covalent interactions. Okay, so in classical dynamic simulations, we have an explicit term, a explicit form, numerical form for each of these non-covalent interactions. Well, the force fields include a large number of parameters. So before running a simulation, the first step is to subject the force field to an extensive and delicate parameterization process, where the results obtained with our force field are compared are being benchmarked against experimental results when available, or to results obtained for simple models using a high-level method, a quantum method. Well, once we have the best parameters for our force field, we can run the simulation where the position of the nuclei and the velocities after a given time interval are obtained by integrating the classical equations of motion. Okay, the Newton's equation. Well, the main problem of classical dynamic simulations, even though we know that we have good force fields that give us accurate macroscopic properties like thermodynamic properties, the main problem of the classical dynamic simulations is the quality of the results obtained at microscopic level. I mean, if I want to study intermolecular interactions, something that occurs at atomic level, okay, the classical force fields are not able to give us very good results. Okay, so in ab initio molecular dynamics, instead of classical laws, we use quantum laws to calculate the energy for a given nuclear disposition. So we solve the Schrödinger equation, okay, and obtain the wave function of the system, and this is done normally using a semi-empirical method or a method based on the formulation, Collingham formulation of density functional theory. However, in ab initio simulations, we don't have an explicit form for each non-covalent interaction, as in the classical simulation. So we have developed, so people have developed useful schemes to decompose the total interaction energy into electrostatic induction. We call induction is the polarization in classical dynamics, Pauli repulsion, and dispersion. Well, these schemes provides a decomposition with in different terms which are solid physical meaning. Okay, these different terms represent accurately the different non-covalent interactions based on the laws that govern the microscopic world. These are the quantum laws. Well, anyway, we still have in ab initio dynamic simulations, we still have to rely on classical mechanics because the nuclear dynamics is still it still depends on the resolution, the integration of the classical equation of motion. Okay, so but this is not a road approximation, but in this case, in the ab initio simulations, we have the potential that the nuclear experience is the correct quantum potential. Okay, it's not obtained from a force field which has a parameterization process. So the ab initio dynamic simulation is free of parameterization. Okay, so it avoids, for example, the compensation of errors between different energy pairs, which is typical of classical dynamic simulation. Well, this slide, I'm showing you the comparison of the main advantages and disadvantages of classical and ab initio dynamic simulation. As a main advantage of classical dynamics is its computational efficiency compared to the very high computational cost of ab initio dynamic simulation. The difference between both is huge and makes that classical dynamic simulations can be run on systems containing thousands of atoms and for simulation times of several nanoseconds or even microseconds. Whereas in ab initio molecular dynamic simulations, ab initio molecular dynamic simulation only allowed to run simulations in systems with a few atoms and for simulation times of some microseconds. On the other hand, the ab initio dynamic simulations incorporate the quantum effects in a reliable way, so in an accurate way, and then it provides more reliable microscopic information. So the problem of classical simulation is microscopic information. So, for example, interactions, intermolecular interactions, non-covalent interactions, that is the topic of my talk. Well, the question is, do we have methods that combine the main advantages of classical and ab initio dynamic simulations? And the answer is yes. These are the methods, the hybrid methods, QM, MM methods, quantum mechanics, molecular mechanics methods, which are a particular example of what we know as multi-scale modeling. Well, the revolution in the understanding of biophysical and biochemical processes at microscopic level that multi-scale modeling brought about was recognized 10 years ago with the awarding of the Chemical Nobel Prize to the pioneers of molecular or multi-scale modeling, Michael Levitt and Ariel Wurtzel, who shared the Nobel Prize with with Martin Karpus, whose contributions to the development of QMM methods were also outstanding. Well, nowadays, a large amount of papers dealing with QMM simulations are published every day, and these are the preferred methods to investigate at microscopic level biochemical and biophysical processes, computationally. Well, this can be considered the first paper published using a QMM method. It was published in 1976 by the Levitt and Warshall, and investigated the reaction between the carbonium ion and enzyme macromolecule, the lysozyme. So the system contained 1,950 atoms. It was a huge system. Impossible to study at quantum level, even for symmetrical methods in that time, in 1976. So the strategy followed by them to investigate the full system was a divide and conquer strategy, where they divided the total system, the full system, into 3 regions. The target region, including the carbonium ion and the nearest atoms from the lysozyme macromolecule. The second region, including the rest of atoms from the lysozyme molecule, and the environment, in this case, the water environment. Well, the target region here was investigated, was treated quantum mechanically with a quantum method, so it's called QM region. The second region was treated classically with a classical force field, so what's called MM region. So M comes from molecular mechanics. And the environment was represented by in this work was represented by an analytic potential. So the most delicate point in QMM methods is not the regions itself, so it's the interaction between the regions. So the interface between the quantum region and the MM region. How I treat the interactions between atoms in the QM region and in the MM region. They introduced what is called the QMM potential. This is what the novelty of this work. We will talk about in detail of this interface and this interaction potential. Okay. So the scheme has not changed significantly so far. In the current methods of QMM methods, the system is still divided in the target region, treated quantum mechanically. The nearest environment to the target region, treated classically, the MM region, and the boundary. Okay, the boundary is what surrounds, for example, could be water or a solvent or something. It's important, the boundary, well, depends. Because many times the boundary effects are overlooked or are accounted for by introducing periodic boundary conditions or a boundary potential. Okay, but the effect of the boundary on the target region, which is an interesting region, okay, it's normally negligible as long as the MM region, the classical region, is large enough. Well, the main problem in QM method then is the description of the interactions between the atoms from the 2 regions, what we call the interface. Okay, so how we can represent these interactions? Well, this is the total effective Hamiltonian of the system, and how the form of this Hamiltonian after the partition of our system into QM and MM regions. So we have the independent QM and MM regions, okay, Hamiltonians, classical, purely classical and purely quantum mechanically. Then we have the interaction between the 2 regions, and we have the boundary. And these are the expressions for each of these terms. Well, we are interested just in this term here, the interaction between QM and MM regions. We have an electrostatic. No, I switch it off.
Your phone.
My phone, no, it's not my phone. It's just a microphone. Well, this is the interesting term here, and includes an electrostatic, a polarization, and a van der Waals term. Okay? So, on the other hand, the methods we normally employ to perform calculations in QM methods include the quantum methods, normally semi-empirical or basic on College and DFT theory for the QM region, electrostatic or polarizable force fields for the classical region. The difference is both include permanent atomic charges in the QM region, but also the polarizable includes atomic induced dipoles. So the polarization of the MM region is also taken into account. And for the interaction between QM and M regions, we can use mechanical, electrostatic, or polarizable embeddings, as I explain you what means these three different kind of embeddings. Okay, but for all these embedding schemes, the van der Waals interactions include the Pauli repulsion and dispersion energy in this case. So the van der Waals interactions between atoms in one region and the other region are always treated classically. Okay, these are what we call short-range interactions. So are important only for small interatomic distances. So they are not relevant. Okay, are only relevant for the atoms included already in the target region. So they are treated classically. No problem for the analysis of non-covalent interaction. So we can forget about this term. Well, in the mechanical embedding, both the electrostatic and the polarization term of the QM and Hamiltonian part are set to 0. So it means that no polarization of the MM region by the QM region, neither the polarization of QM region by MM region, nor polarization of MM region by the QM region is taken into account. So it's like no interface because we are not including not really including the interactions part of the van der Waals. So this is the worst embedding we can use, of course, but it's computationally very efficient. Well, in the electrostatic embedding, we include the charges from the classical region in the electrostatic term of the interaction between QM and M region. So here we are considering the polarization of the electron density in the QM region by these charges. However, the polarization term is set to 0 again. So we don't consider the polarization of the MM region because of the QM region. Okay, only polarization of the most important part, okay, is the QM region. So this is the most used embedding scheme because of a very good compromise between accuracy and computational. And finally, in the polarizable embedding, we also include induced atomic charges in the classical region, in the MM region. So we are also considering the polarization of the MM region by the QM region. So mutual polarization between both regions. This is more accurate, but also much more computationally demanding because the process of obtaining these charges is a self-consistent process where, okay, the charges of the classical region polarizes the QM region, and then this polarization is transmitted back to the MM region anti-convergent. So it's computationally expensive. That's why electrostatic embeddings are normally more frequently used than polarizable. Well, if we want to do a simulation, a dynamic QM simulation, the first thing we have to do is to choose the QM region. Okay, so in this example, this is the Schweitzer ion, it's a glycine molecule. Well, in chemistry, Schweitzer ion is a neutral molecule, but with a positive charge and negative charge located in different atomic sites. So it's neutral, but it's a highly polar system. Well, if we want to simulate the solvation of this Schweitzer ion by water, here we have 3,000 water molecules, we can choose different regions, 2 M region sites. The first one is as a glycine molecule, the second one includes glycine and 20 molecules, water molecules, and the third one includes glycine plus 100 water molecules. Well, here we have to define also the interface. In this case, it's very easy because the difference is just the number of water molecules I include in the QM region. So I don't have to break bonds. Put more molecules and define my interface. But for example, in a macromolecule like a protein, okay, when I define the QM region, I have to cut bonds, to break bonds, okay? So in this case, the atoms in the QM region, its nature changes drastically, okay, because I am removing the atom which is bonded to it, and I'm putting this atom in the MM region, okay? In this case, I have three options, three approaches. Okay, one of them is more used than the others because of its simplicity. It's the linked atom approach, where in this linked atom approach, the atoms in the Q region are saturated by a hydrogen atom or a methane group to keep as much as possible the nature of the atom. Okay. Well, let's talk about now about the different kind of non-covalent interactions. The QM methods are very useful to investigate intermolecular interactions. Intermolecular interactions, as I mentioned at the beginning, are very important for many biological processes or biophysical and biochemical processes. They are, sorry. I was here, sorry. Yeah. This, they play a key role, for example, in the study of physical properties, okay, like the capacity, viscosity, etc. In the study of the state of matter aggregation, surface-like processes, mixture solutions, protein folding. Well, in general, they influence any process taking place in a condensed phase. So, are very, very important to the non-covalent interactions. Okay. So the classification, the most general classification of non-covalent interactions is done in terms of its range of action. Okay, so we have long-range interactions where we include electrostatic and inductive, so they vanish only a large distance, interatomic distances. Medium-range interactions where we include only dispersion, and short-range interactions where we find exchange and repulsion interactions which both conform what we call Pauli repulsion. Okay, and we have also in short range other interactions that has not an ambiguous definition, like for example, hydrogen bonds or charge transfer interactions. Okay, they are very important, but hydrogen bonds can be considered a combination of partially electrostatic and partially covalent interactions. And charge transfer interactions are already included within the inductive interactions, but for nearby atoms. So they are not really new. Well, this non-covalent interaction can also be classified in terms of its nature. So if the interaction has a classical equivalent, okay, they are considered classical interactions. Electrostatic and inductive, for example. They have a classical, can be calculated classically with explicit expressions. However, if they have only a quantum interpretation, they are considered quantum interactions. And here we find the dispersion and the Pauli repulsion interactions. Obviously, these quantum interactions are those who are represented by the classical force fields. And the main problem, the main responsible of the failing of these classical force fields in simulations, chemical simulations. Well, since I have tried to make clear that we need quantum methods to study non-covalent interactions, I will introduce you in the two approaches employed to calculate and to investigate these non-covalent interactions at quantum level. So the first one is the supermolecular approach, where the interaction energy between two molecules, A and B, or two molecular fragments, is calculated as the difference between the energy of the complex minus the energies of the isolated molecules. It's a very simple idea. Okay, but this supermolecular approach, combined with what we call variational EDA, it means energy decomposition analysis schemes, allows to decompose the total interaction energy to electrostatic, Pauli, and polarization. The problem of these variational schemes is that they don't provide a dispersion energy. So you cannot extract dispersion energy from the polarization energy. The second approach is based on perturbation theory. The perturbation theory means that much more computationally cost, but this theory allows to split the polarization energy into induction and dispersion. Okay. Well, our scheme, our methodology, the one we have developed in our lab, is based on the fragmentation of the total electron density into isolated fragment electron densities and deformation densities associated with the different non-covalent interactions. Well, it takes profit of both approaches, variational and perturbational, because we use a variational scheme to obtain electrostatic, Pauli repulsion, and polarization, and then we apply the second order perturbation theory to split this polarization to induction and dispersion. It's a combination of both. Well, so using this fragmentation, we obtain all the terms: electrostatic, repulsion, exchange, and polarization. And of course, I'm not going to get into the equations. Okay. The only thing I want to make clear is this fragmentation of the electron density leads unequivocally to a fragmentation of the interaction, and to the terms we are interested. Well, additionally, this repulsion and exchange has the same physical origin. They are usually merged into only one term, which is the Pauli repulsion energy, and have the same physical origin. The origin is the well-known quantum mechanical principle, the Pauli exclusion principle. Those who have some knowledge of quantum mechanics knows perfectly what Pauli exclusion principle is. So they can be analyzed separately, but they usually included in one term. So, and also I mentioned it before, that we use the second order perturbation theory to split polarization into induction. Then we have the final decomposition, electrostatic, Pauli, induction, and dispersion. Well, let me make a small paragraph to explain in more detail what the Pauli repulsion is, because Pauli repulsion is the Achilles heel of classical simulations. Okay, it's the main responsible for the failing of the classical force fields. Well, the Pauli repulsion includes two terms. One repulsive and one attractive. The repulsive term comes from the overlapping between electrons from different fragments. Okay, when two electrons from different fragments of the same spin are forced to share the same space region, okay, they confront with the Pauli exclusion principle. The Pauli exclusion principle tells us that two electrons with the same spin cannot occupy the same point of the space. It's a purely quantum effect. So what happens? We force the fragments to overlap the electrons in the spin. So there is a deflection of electron density in the overlapping region to avoid this overlap. Okay. So this is a repulsive term because the energy cost is positive. Okay. Well, but the Pauli exclusion principle also entails the electron exchange between electrons of the same spin. Electron exchange is also another quantum effect. Okay, I'm not going to explain what consists, but what I can tell you is that it's always stabilized in an electron system. Okay, the electron exchange always decreases the energy. So we have a stabilization of the complex because of this effect. But in non-covalent interactions, spin repulsion is always larger than exchange, so we have a net repulsive interaction. This effect is illustrated here on the left side, on the right side of this slide, by the Pauli density. Pauli density obtained with our method. So we can see here that the negative density is represented by a yellow color, and the positive density represented by a magenta color. This is for dimer water-to-water molecules interacting, and this is a pyridine molecule, well, a molecule absorbed on a graphene surface. Okay, we can see that there is always a deflection of electrons in the center and accumulation of electrons in the molecules because of this, trying to avoid the overlapping. Okay. Well, in classical force fields, the Pauli repulsion is included in the Lennard potential in this term here, the positive one, this with the power is 12. Okay. Well, one of the most simple examples of non-covalent interactions, the interaction between two neon atoms. Okay, this is one of the most simple examples of non-covalent interactions. This is shown here. Here in this plot, we compare the total interaction energy, the repulsive part, so Pauli repulsion, and the attractive part, which in this case is just dispersion energy, obtaining with the Lennard potential and obtaining with a high-level quantum method. Okay, so it's the correct result. As we can see, the Lennard potential reproduces very well the total interaction energy. This is the total interaction. This is the repulsive term positive, and this is the attractive. However, the separate terms are not well represented. by the Lennard-Jones potential. So what we have here, we have a compensation of errors, which in this simple case leads to a good description of the potential well for the total interaction. But in a more complex system, like biological biomolecules, okay, this can also lead to an error in the total interaction energy. So making that the classical simulation. Well, the methodology based on this information density also allows to visualize the short range and long range character of these intermolecular interactions. In this example on the right side of the slide, we compare the Pauli density and the polarization density. So the density associated to the Pauli repulsion and to the polarization interaction, okay, for different cutoffs for arising from the interaction of a polychlorinated dioxin with a membrane, lipid membrane. Okay, well, you can see that the Pauli density vanishes relatively at a relatively short interatomic distances. So we need a small QM region size to reproduce, to account for these interactions. But in the case of polarization density, the polarization density vanishes at a relatively longer interatomic distance. So we need a larger QM region to represent this interaction. So it's important to analyze what happened with each term to finally choose a correct QM region to perform a QM simulation. Well, the QM region size is a major problem in these methods. So in this slide, I'm going to show you the importance of including the classical environment to calculate interaction energies. Okay, the example chosen is the ammonium cation surrounded by 100 molecules, water molecules in the QM region. We have 2,900 molecules in the MM region, but they are not shown here, of course. Well, comparing the results obtained at QM level with the classical region, with the classical water molecules, with calculations, with pure QM calculations, so removing the classical region, okay, we have found very important differences in the total interaction energy by around 40 kilocalories. That which mainly comes from the electrostatic term and the induction terms. These are the long-range energies. Okay, this is not an unexpected result because the QM region is large enough to get to represent well the Pauli, short-range Pauli and medium-range dispersion interactions. So the conclusion here is that we need to, it's necessary to include the classical environment, okay, at the time of studying the molecular interaction, and it's also important in the decomposition we do later. So in the electrostatic and different terms, it's also very important to include the potential, the potential created by this classical region. So the strategy we follow is to include this potential in our methodology is including the potential in the nuclear potential of the fragment that contains the classical environment. In this scheme, this is the fragment B. Fragment B includes the quantum region, part of the quantum region, and the classical region. And in the center, we have the other fragment A, only the quantum region. Well, this potential may include atomic charges only, or atomic charges plus induced atomic dipoles, depending on the type of embedding we want to use, electrostatic or polarizer. Well, let me tell you something about the implementation of our methodology in the software. Okay. So even though there are other software packages that includes a module to perform structure calculations, classical simulations, perform energy decomposition analysis, none of them allows to perform energy decomposition analysis at QM level, only at QM levels, only for pure quantum calculation. So there was a need to develop a software to perform energy decomposition analysis, saying all the interaction energies and the different energy terms at QM level. Well, And it's just a summary of the main features of the software. So the different mathematical operations are performed, typical material organization, orthogonalization of orbitals. Well, these mathematical operations. Well, the programming language employed for the main program is Fortran, okay, Fortran slow programming language, but it's extensively used 10 minutes. 10 minutes without questions or with questions? Without questions, okay. So, well, it's written in Fortran language, is extensively used in other software packages for electronic structure calculations and classical simulations, but also includes some Python scripting, okay, to deal with other standard programs. We use standard programs to perform the quantum calculations and the classical calculations. The program only do later the energy decomposition analysis. Okay, so it has an interface. For the moment, it has an interface with the most used programs in computational chemistry, I think, for electronic structure calculations, or for QM quantum mechanics calculations, Gaussian, and for classical dynamic simulations, Ampere. Okay. Well, and this is a software project we have started very recently to improve the capabilities of the software we have right now. This is the bio-EDA project, and this is the flow chart summarizing the main operations of the program. But these are the improvements, okay, with respect to the software we have at this moment. So we want to we are creating a software with a broad interface with many softwares for electronic structure calculation, for quantum calculation, and also for classical simulations. Then we are going to include a module to study in molecular interactions, intermolecular interactions, non-covalent interactions, not only for ground state, but also for excited states. This is very important to study photophysical, photochemical processes, which are very frequently, for example, in phototherapy treatments and stuff. Well, then some automatization for the analysis of optimal conversion size, statistical analysis along the trajectory in a dynamic simulation. So the question not only investigate the intermolecular interactions, the non-covalent interactions for a given geometry, but along a trajectory. Okay, so the program is going to perform energy composition analysis at different geometries along a molecular dynamic simulations, and then give an statistical. Well, I'm going to finish. I'm going to show you very fast some results we have obtained with our program. Okay, this is an example of an ammonium cation surrounded by 3,000 water molecules. Okay, here we have performed this study to investigate the importance of the QM region size in the QM intermolecular interactions, okay, calculated at QM level. So this is the representation of the different interaction energy terms and the total interaction energy, okay, the convergence with the number of water molecules included in the QM region. Okay, for the ammonium cation, we have found that we need at least 160 molecules, okay, to converge the electrostatic, the long range of the electrostatic interaction energy and the total interaction. Well, for the sake of comparison, we also performed the same analysis, but for pure QM calculations, okay, removing the classical region. And as you can see, the electrostatic energy and the total interaction energy, the red line and the blue line here, are far to be converged, even for a QM region size, a QM region including 240 water molecules. So it's very important to include the classical region to investigate the interactions in this kind of thing. Well, how much time, Andrea? 5 minutes. Okay. Well, I think I'm going to skip it, so it's more something similar to ammonium. And I would like to show you. Okay. Well, I would like to show you another simulation we have also investigated not only solvated molecules, but also systems, processes where, for example, this is a cisplatin molecule crossing a cell membrane, where the membrane was simulated using a model of lipid layer, including 128 lipid molecules. Okay, this is the classical simulation. In the classical simulation, well, cisplatin is a chemical compound sensibly used in chemotherapy treatments. Okay, so the classical simulation, the permeation of the cisplatin to the membrane goes through an energy minimum in the hydrophilic region of the membrane, the orange region here, and a maximum, the energy maximum at the center of the membrane, which is the highest hydrophobic region of the membrane. So we have also investigated here first the convergence of the interaction energy terms with the size of the QM region. In this case, we have included more and more lipid molecules in the QM region and see when the results converge. Okay. As we can see here, we found the same comparing this is for the minimum, for the maximum. This is the QM calculations, and these are calculations included also in electrostatic embedding. And we have found that for QM calculations, even with 8 lipid molecules are large molecules, with 8 lipid molecules, we don't get all the energy terms convergent. However, if we include an electrostatic embedding, so the classical region, we have found that the energy terms are convergent with 6 here, with 6 lipid molecules. So we have also analyzed the distribution of the energies along the trajectory. I mentioned it before. So we took a series of X-spacing geometries along the trajectory and analyzed all the energy terms and plotted the distribution of the energies. Here we can see the distribution of the energies for the minimum, maximum, and the average energies and the standard deviations. And we found that for the energy distributions, we found that the higher the energy, the broader the distribution. Okay, this is not surprisingly that in the Pauli proportion, this is the yellow line, the Pauli proportion shows much broader distribution than the rest because it's a short range term and depends more in the interatomic distances and the changes in atomic distances with along the trajectory. So it has a very low profile. As for the most interesting is that as for the average energies, we found very important discrepancies with the classical simulations. So that reflected an error compensation between electrostatic and non-electrostatic terms. So which came mainly from a large underestimation of the Pauli proportion by the classical force field. So here we found another failing of classical force field. Well, to finish my presentation, I would like to thank the organizations and institutions that have partially funded this research, and I would like to thank to my colleagues in the Quantum Chemistry Group from the University of Vigo, Álvaro Pérez, Nicolás Ramos, José Hermida, and colleagues from the MoBioChem group from the Autonomous University of Madrid. They did the Python scripting for our software. It's called MM-EDA NCI software. Gustavo Cárdenas, Juan José Nogueira, and Lorena Ruan. And just to definitively finish my presentation, I would like to show you this. I think this nice simulation. This is an ab initio molecular dynamics simulation. It has a lot of atoms here. It was 3 months of calculation for this simulation. For the simulation, they are only some picoseconds. Okay? And this is the bromide anion, it's a bromide anion, trapped within a tweezer cavity, a molecular tweezer cavity. It's a neutral molecule, this tweezer, and surrounded by water via. This is a nice example of cooperativity between hydrogen bonds and dispersion interactions between the tweezer and the bromide anion. It's this cooperativity makes the bromide anion prefer to stay inside the cavity than in its more natural water environment as an anion, okay, by an stability of more than 100 kilocals per mole. What's my point here? That twisters like this one, have been already synthesized and are used for what we call in chemistry, it's hot topic, which is anion recognition, but not so efficient like this one. So quantum computation, computational chemistry, it's a very useful tool that to guide the experiment, that is to synthesize compounds with an improved capability. Very nice example of this research. Okay, so thank you very much for your kind attention.
Thank you, Marcos. Now it's time for a question. You have some questions. Okay, I have a question, more curiosity than others. And you briefly explained that one of you told us in your presentation of the QMM method that the interface and the boundary are the critical regions. My question is, what if you need in your simulation to define more than just one QM region, for example? Is that possible?
Are the QM regions different? So in a protein?
For example, in a protein, you want to just focus 2 or 3 sites.
What you do normally in this case is to cut the system into systems and perform different studies. Of course, you can do it. You can define two regions. But I don't think the softwares
are ready for this. But in principle, you should consider also interaction, QM, interaction in that case.
Yeah. Well, but then if the QM regions are close enough to interact with each other, I don't think it makes sense. So it should be better to behave analysis with regions.
Okay.
Because, well, but anyway, interactions between regions of different nature, so I don't think it's a problem, because the Hamiltonian is the same.
The molecular, no? If you have to do molecules interaction.
If you choose the same method, your method to study this, so you know that, for example, Gaussian allows you to split also in 3 or more regions with different QM levels of calculation.
Okay.
Yeah, but this is for onion method. This is another type of method that you don't have an interface really.
Okay, so let's say thank you to Marcos for this very interesting presentation, and I will think Thank you, Marcos. I think we can do home or to other sessions. And later to the social media. Don't miss the bus. 7:30. Thank you.